Today. I'm glad that you are all joining us for the second day. Yesterday we had an excellent meeting and we had excellent questions, and the questions that could not be answered because of time, we will be directing the answers directly from the speakers to them. So right now we're going to be starting our third session, and it's indeed my pleasure to introduce John Lynch. He's the Vice President of Orkway Paving Corporation in Watseka, Illinois. For the last 35 years, he has held various roles, including working on the paving crew and in the quality control lab, as well as qualifying estimation. He also serves on the IAPA Board of Directors, and previously he was the president of that board. So John is a good friend, and we're very, very pleased to have him with us here and agreed to moderate the next session. John, the floor is yours.
Thank you. Good morning, Ahmad, and thank you. We all thank you for making this happen in such a difficult year and circumstances, but this seems to be going very well, so thank you. We are on day 2 of our program, and our first presenter is with the Redefining Value and Sustainability and Resilience is Joseph Shackett. Joseph serves as the technical lead for Eco Label, NAPA's environmental product declaration program for asphalt mixtures. His role at NAPA also includes directing research projects related to asphalt pavement sustainability and resilience, educating the asphalt industry about sustainability and how to incorporate it into organizations, and working with external shareholders such as government agencies and green rating system. Joseph, the Zoom meeting's yours.
Thank you. I'm just going to go ahead and share my screen. I appreciate the introduction, and I'd like to thank Ahmad for inviting me to present here. I'm really happy to be here and honored for that matter. I'm excited to see what kind of questions we get out of this presentation. So I'm going to go into presentation mode, and hopefully that works without any flaws. So again, my name is Joseph Shackett. I'm with the National Asphalt Pavement Association. Today we're going to talk about redefining value through the lens of sustainability and resilience. So first I want to open with a little introduction about NAPA. We are the only trade association that represents exclusively the interests of the asphalt pavement industry. We have more than 1,100 member companies, which are a combination of asphalt mix producers and affiliated industries such as paving contractors, equipment producers, and material suppliers. Some of what we do, we have a really strong research and engineering team. This is a picture here of the NCAT test track at the National Center for Asphalt Technology at Auburn University down in Alabama. We support NCAT through our research activities, and also work with other agencies, Federal Highways and Federal Aviation Administration, and other agencies to support research and implementation of new technologies and that sort of thing. We have a education and member services group, and they handle things like our meetings, webinars, which have been really popular this past year for, I think, obvious reasons, and other educational activities like that. Member services include awards, diamond combinations, and that sort of thing. And the last thing we do, we have a really good federal advocacy team. So this includes, lobbying on Capitol Hill for support of highway and airport investments, and also addressing environmental health and safety regulatory issues. So there's a general overview of NAPA in case you have any kind of curiosity about that. So I'm going to start with sustainability, and I'll open this with saying that sustainability is not a new concept. This is Cicero, who was a contemporary of Julius Caesar, 44 BC, ancient times by this day. In one of his writings, he was talking about Statius, who was a poet, and Statius, one of his statements was he plants his trees to serve a race to come. And this is the idea that you're looking out for the next generation behind you. And you're not just thinking about yourself, but future generations. And I think many, including myself, would argue that this is a sign of a civilized society, where you're looking forward to future generations. When you fast forward about, a quick 2,000 years, I'm going to mention here, this is what Federal Highways Administration defines as a sustainable pavement. And they say sustainable pavements should achieve the engineering goals for which they were constructed. And I think that's an important kind of first step. Now, if you can't at least do that, then you're doing something wrong. Pavements should preserve and ideally restore surrounding ecosystems. And you might think, how does a pavement restore an ecosystem? And here I would say, if you think about porous pavements as an example, where you're taking rainwater instead of running it off into the local streams, rivers, and other water bodies, it's going back into the groundwater and being recharged. You're restoring that natural ecological function or hydrological function and improving water quality and restoring that kind of aquatic habitat in some ways. So I think that's an example of thinking about pavements as a restorative function. And then the third thing here is using financial, human, and environmental resources economically. I like to think of this as kind of a mom's apple pie thing. If we're not using our resources frugally or with conscious of not overusing our resources, then we're doing something wrong. And then the last one is meeting human needs such as health, safety, equity, employment, comfort, and happiness. And I like this last one here on happiness. You might think, how can a pavement make you happy? Well, I can tell you how a pavement can make me unhappy, and that's when it's not been maintained, it's rough, and you're going, and your car is getting beat up. That makes me pretty unhappy. But when you have a nice, quality, smooth pavement, in my mind, made out of asphalt, that's going to make me happy. So just a perspective on thinking about sustainability of pavements. Another perspective on sustainability, which many people are familiar with, is the triple bottom line of concept. And this is a Venn diagram. I'm a big fan of the Venn diagrams because it's a good visual of kind of looking at what's going on and what the overlaps are, showing the economic, social, and environmental aspects of really any system that you're looking at. When you apply this to pavements, you can think in economic terms of straightforward agency costs, whether that's first cost or life cycle cost, and user costs. So it might be work zone user delay and that kind of thing. And these are often incorporated into a life cycle cost assessment or LCCA analysis. And then you can also think about not just the cost, but the benefits. So pavements, roadways, networks in general provide for mobility, commerce, freight, transport, and that sort of thing. So there's a lot of benefits associated with pavements as well you can think about. From a social perspective, you can look at safety, like skid resistance. If you're using a novel material or novel mix design or something like that, you want to make sure that the cars driving it on that pavement are safe. And then another way to look at the social aspects of a pavement is the workforce. So is your workforce earning a living wage? What's the kind of equity within your workforce and other considerations? And of course, workforce occupational safety is a component of that as well. And from the environmental side, this is looking at things like emissions, whether it's greenhouse gas emissions or smog forming gases or acid rain forming gases, those sort of emissions. Runoff, we talked about porous pavements just a minute ago, materials, and this would be circularity, the use of recycled materials. These three aspects and others are often looked at through the lens of a life cycle assessment, or LCA, which is growing in popularity amongst agencies. And a lot of agencies are kind of expressing interest in incorporating LCA into their kind of pavement management, pavement design, and overall asset management programs. So these are all ways to kind of think about sustainability as they apply to pavements. Now, I would be remiss to talk about sustainability without invoking the term of the pavement life cycle, or the concept of the pavement life cycle. And we like to think about the life cycle starting with maybe design, but also materials, extracting raw materials, whether it's aggregates or binders, the petroleum for asphalt binders or additives, manufacturing those raw materials, transporting them to the plant, and then mixed production. So these three components here are typically referred to as the cradle to gate stages of the pavement life cycle. Once you leave the gate of the plant, this is kind of leaving the mix producer's kind of area of control in many cases. You have transportation to your job site, construction, paving operations, moving on to the use phase. That would include things like vehicle fuel consumption, maybe lighting, and other things like that. Maintenance and rehabilitation, so this would be your mill and overlay, pavement preservation, and those sorts of activities, and then end of life. And in this industry, we're a pretty highly circular economy in the sense that most of the materials that are removed at end of life are put right back into the mix. So that's a real positive kind of looking at this overall pavement life cycle. So I want to kind of talk for a minute about some of the sustainability strategies, kind of looking at all these different life cycle stages and concepts that you can apply to pavements. Now, looking at NCHRP this past year, they published the Sustainable Highway Construction Guidebook, and this is a really, actually really excellent read. It's for a lengthy NCHRP report. It's actually a pretty easy read. And they identify 77 or so sustainable construction practices that can be applied in the highway industry. And many of them are directly applicable to pavements. And I've just highlighted a few of them here, starting with smoothness, quality or durability, long life pavements, recycled materials, including wrap, density, including use of warm mix as a compaction aid, longitudinal joints, segregation, tack coats. These are all, pretty, I would say, fundamental foundational aspects of pavement construction and design and mixed production. And the first four here, I'm going to go into in a little bit more detail because I think it's worth exploring kind of where the opportunities are for creating value. So starting with smoothness. Smoothness can impact vehicle wear and tear. It can impact pavement wear and tear. It can impact fuel efficiency. And I'll stop here for a second because, smoothness is one of the components, probably the leading component associated with pavement rolling resistance. You can make smoother pavements. You're going to make the cars driving on that pavement more fuel efficient. And this is not an insignificant value here. When you look at the total life cycle, like I showed before, and all the emissions from a greenhouse gas emissions perspective, the lion's share, probably 90% or more in many cases, of that impact is going to be from the vehicles operating on the pavement itself over a long, say, 30 or 40-year life cycle. Now, this will vary depending on how much traffic the road gets and that sort of thing, but it's a really significant factor. In fact, if you could reduce the fuel consumption of the nation's fleet of vehicles by 1% by having smoother, well-maintained roads, that would be equivalent to about all of the emissions from material extraction and mixed production combined for the entire U.S. industry, with just a 1% improvement in fuel efficiency. So this is a really big deal. And then other factors, noise, safety, if you can improve these things, you're going to improve, create value for the people driving on the roads and nearby residents or businesses next to a road. So these are all things to think about with respect to smoothness. The next one here I want to talk about is long life pavement design or perpetual pavements. Now, this is the concept of designing a pavement so that it's never going to actually experience structural rutting or cracking. You're going to have to maintain the surface wearing course, obviously, but you shouldn't have to go in and do a reconstruction or redo the base and that sort of thing. To design this pavement, you're typically going to have a higher initial cost for the agency because you're typically designing a pavement with a thicker section than normal. But you're going to benefit over the life cycle by reduced maintenance costs because you're not having to go in and reconstruct that pavement in the future. And then in some cases, as shown here, you can significantly reduce the work zone user costs. Now, again, this will vary depending on individual projects. A rural highway in Illinois is going to be really different than an urban congested highway outside of Chicago. So that work done user cost can be really significant as the kind of level of congestion goes up. And so I'm going to turn here now to some material considerations. And if you're not aware, I think most people here probably are aware, for the last 10 years, NAPA has been conducting a survey of industry on use of recycled materials and warm mix asphalt technologies. We have a great turnout on this. We get more than 1,000 plants every year that submit data. So it's a really good kind of snapshot of what's going on in the industry. Now, with respect to RAP, this graph here shows, the orange line shows the amount of RAP used every year since 2009. And that corresponds to the secondary y-axis on the right side of your screen. When we started in 2009, about 55 million tons of RAP were being used to put in new mixes. This past year, 2019, almost 90 million tons. And it's not just the total amount of RAP that's gone up, because as you can see, total mix production has also gone up. But the amount of RAP in an average mix has gone up from about 15% or so in 2009 to close to 21% this past year. So, the amount of RAP being used in pavements is increasing. And as long as we can continue to increase that and maintain quality of our mix, quality of the pavement, and not degrade quality, then that's going to be a net positive. In fact, when you look at 2019, the use of RAP reduced the extraction of petroleum for liquid asphalt binder by 24 million barrels. And it reduced the amount of aggregate that had to be blasted out of the ground and crushed and screened by 84 million tons. These resulted in a net savings of 2.4 million tons of greenhouse gas emissions, approximately 500,000 cars worth of greenhouse gas emissions, and over $3 billion in economic savings. So clearly we're creating value through using RAP. And this is a kind of really good direct measure of that. The other thing we look at in the survey is use of warm mix asphalt technologies. When we started this survey in 2009, only about 5% of the mix produced in the US was using a warm mix technology. Past 3 years, we've leveled off at about 40% of total mix production, which is pretty significant. Now, I will say that only about half of that is actually produced at a reduced temperature, meaning the other half, or 20% of the mix produced, is using a warm mix technology as a compaction aid. Now, if you're getting better compaction on your job because you have this warm mix technology, and yet that better compaction is going to translate to better pavement durability and better pavement life, even that I think is a significant win from a sustainability perspective. The other thing on this warm mix technologies, which I don't have a graph for, but it's in our report and it's really worth thinking about and looking at. When we started the early years of this, almost everyone was using plant foaming technologies. Now it's about half of the warm mix produced is using plant foaming, and the other half is using a chemical additive. And in a lot of cases, that chemical additive is also doubling as an anti-strip agent. So if you're getting two functions out of one material as an anti-strip and as a warm mix, then that's also, I think, beneficial for our industry. So this is, I think, really, warm mix is a great technology, and I'm really glad to see the progress our industry has seen over the last decade or so. Now, the survey itself, the next survey is going to open on January 1st, which is coming up in just a few weeks. So if you're a mix producer, I encourage you to please plan to participate in the survey. This is funded by the Federal Highways Administration. So the more plants we get participating in this, that's really great for our partnership with Federal Highways. And there are lots of folks that look at and use the data in these from the survey, including the EPA and research institutions and other agencies. So having your participation is really great. It's a great New Year's resolution to say, hey, we're going to submit data for our plants for NAPA survey. So I want to talk for a few minutes about some of the sustainability resources that NAPA has available. We have paving awards. We have operational excellence awards. These are awarded for quality, safety, community involvement, environmental excellence. These are all sustainability, kind of related to sustainability. It's a great way for a company to showcase its commitment to quality and its leadership in the industry. And then we also have the Diamond program. So you can achieve Diamond achievement for your plant, Diamond sustainable if you're a step above. And then we have Diamond for terminals, paving, and quality. So another way to kind of demonstrate your leadership in the industry. And then the other thing with another program that NAPA offers is our EPD program, which I have a lot of responsibility for. I could talk about this for half a day if you wanted to, but we don't have that amount of time. But the EPD is a way to kind of measure and quantify the environmental impacts associated with producing asphalt mixes. And it's a great way to look at your supply chains and plant operations and benchmark your operations and improve them over time. And it's also a marketing opportunity. You have customers that are doing LEED projects or other green rating systems, and they can earn credits by collecting EPDs for products they use on their projects. Some of the other NAPA resources that are available through our website, many of these are free. Some of them have a modest fee attached to them. We have the practical guide to sustainable asphalt pavements, guidance on porous pavements, guidance on LEED and other green rating systems. We have a greenhouse gas calculator, which is free and easy to use. It's really just looking at the gate-to-gate emissions. We have a recycled materials and war mix survey, which I mentioned previously. Lots of publications on RAP, recycled shingles, stone matrix asphalt, open graded friction courses, all kinds of things like that. Lots of good publications and webinars, both live and recorded webinars you can download. I'm going to pivot here now and talk about resiliency for a few minutes. And when we talk about resiliency, first of all, what is resilience? What is this? And Federal Highways defines resilience as the ability to anticipate, prepare for, and adapt to changing conditions and withstand, respond to, and recover rapidly from disruptions. I think a lot of people look at resilience and they think about, you got to be strong and tough and survive, but it's not just about survivability or strength. It's also about the recovery and how quickly you rebound. And this graph is a way that many people are thinking about how do you quantify resiliency. And if you think about a kind of base kind of level of service, and then you have a disruption, that disruption is going to reduce the level of service. And then over time, you're going to recover and restore that service. And if you quantify, if you kind of integrate the area under the curve there, you could quantify resiliency. So that's the way that some people are thinking about quantifying resilience. Now, as it applies to asphalt pavements, many people are thinking about natural disasters. Hurricanes, well, you don't really deal with those in Illinois, or earthquakes for that matter, but floods, tornadoes, you might have to deal with. These types of events they can damage roads and affect mobility, emergency services, access to medical care and food supplies, commerce, and the list goes on. And the key here when you have these events is to quickly restore service. By the way, if you look up resilience on Google, you're going to find all kinds of things. It might be talking about personal resilience here, and that's where I put this cover from a kind of self-help book, which I thought was interesting. And there's some really great examples of responding to these natural disasters. Here's an event that occurred in Alaska a couple of years ago. It was an earthquake, and all 8 of the major roads that connect Anchorage to its surrounding communities were damaged. And all of these were repaired within 5 days. And this is pretty significant damage, and this was fixed within 5 days. Now, this is in December in Alaska. The asphalt plants were shut down already. The asphalt binder was cold. It was below freezing. So they had to fire up the plants, get everything heated up, fix the roads, pave the roads, and they did all that in just a few days. And a big part of what made that happen was the industry, the community, the construction community got together and said, who can do what? Let's get it done. And they did a lot of the work before they even had contracts in place with the agency. And that's because of the level of trust between the agency and the construction community in that area. So that's, I think, an important thing to think about. Another example of speed of construction being an important kind of factor in recovering from a big impact. This is about the same time in October of 2018, Hurricane Michael surprised the panhandle of Florida. It was supposed to come as a Cat 1, and in the last 24 hours, it ramped up to a Cat 4 or Cat 5, and it really caused a lot of damage. There was a 40-mile stretch of highway on US 98 that was affected, about 15 miles of which looked sort of like this. When they did the repair work over the next several months, they were able to kind of restore service and reopen the lanes of traffic every day. And that's a really important way to kind of maintain mobility. Similar situation happened in Colorado, 2013. This is a massive flooding event that occurred. I think they received 17 inches of rain in a few days time period. The recovery, this flood occurred in September of 2013. And when the agency started to, just figure out how to fix this, their goal was to just get a gravel road open to the residents that this highway serves before winter set in. This is the fall and high elevations in Colorado, and it's cold. There's not a lot of sunlight. They're in steep canyons. They used warm mix. They were traveling more than 3 hours away for their haul distance for their mix. So by using warm mix, they were able to apply their mix, to pave, get compaction, and get a quality pavement put in. And they did all this before the winter set in, kind of exceeding expectations from the agency. So great response strategy. And then, resilience isn't just about these dramatic events. It's also thinking about the future and, how climate change might affect typical weather conditions. So here's an example, looking at, different cities across the country and what might their weather look like in 50 years or so. Now, I live near Washington, D.C., and we already have pretty hot and unbearable summers, and to imagine that they're going to turn into something like Texas in another 50 years is pretty interesting. Where you are in Chicago or Illinois, Minneapolis is a good example there. The weather in the future might be more like, Iowa or Kansas City or something like that. So when you're looking at these changes, they might be using different binder grades as the temperature warms up. And if you plan on this, if you look at your pavement design and incorporate climate models to think about what's the future weather going to look like, you can select the right binder grades, design your pavements properly, and do it very cost effectively as long as you're staying ahead of the game. And the message here is to stay ahead of the game, think about the future, and start putting together the analysis you need to incorporate climate models into your pavement design programs. So that's kind of a key aspect there. And I'm going to kind of close with just a few resilience-related resources. These are all published by Federal Highways Administration. You'll have access to this to these slides, so you'll be able to kind of take a look at these on your own time. And that's really all I have to talk about. And if there's any questions, I'm happy to answer. I think if we have a couple minutes, I'd be happy to answer any questions.
Yes, we have questions. Well, we have time for a couple of questions, or one, I think. You can submit that in the Q&A. You can submit that in the chat, or you can raise your hand to submit your questions. For now, I do have a question. Maybe we can start with that. I would like to know how you think agencies can motivate contractors to adapt sustainable strategies in their construction methods. Because I think this is a challenge that we all have to tackle together. Maybe you can elaborate on that.
Yeah, I think it's really important to think about when you're talking about sustainability, typically somebody's going to benefit. And if the contractor is going to benefit, for example, with RAP, reducing your cost by using recycled materials, or warm mix sometimes, if you're going to reduce your energy consumption. The important thing for agencies is to allow for that, right? Through specifications. Oh, sorry, my 2-year-old wants to say hi to everyone here. And so I think if you can identify who's going to benefit and then allow that to occur. So in some cases, if the public is going to benefit, it might be really costly for a contractor to do some sort of change that's going to improve kind of a public benefit. And so that's a real, so in that case, it's a matter of contracting and incentivizing the contractor to do those things. And I apologize. I don't know what's going on with my little one here. Sorry about that. And that's, I guess, my answer to that question.
Okay. So we do have another question from Don Rosenbarger from Delta Companies. It says, how do we best use the sustainability and environmental stewardship of asphalt pavement in the LCCA discussion?
Sorry, can you repeat that real quick?
It says, I think you have it in the chat too. It says, how do we best use the sustainability and environmental stewardship of asphalt pavement in the LCCA discussion?
Yeah, I think that's a good question. You know, one of the key things I think is making sure you're including user costs in the LCCA. But some things are not going to be covered in the LCCA. So if you're talking about carbon emissions, for instance, greenhouse gas emissions, you know, that isn't going to be quantified in an LCCA under this kind of you know, environment where there isn't a direct cost associated with carbon emissions. So, so in some cases, if you want to bring in the social and environmental aspects, to some extent, you know, user cost can address that. But on the other side, you know, on the other side of that, LCCA maybe isn't the right framework, and that's where agencies are looking at life cycle assessment and other kind of frameworks for that.
Perfect, thank you. We have a couple more in the QA, but in benefit of time, we're going to move on. I'm going to give it back to John. But Joseph, if you could type the answers to the questions in the Q&A, that would be great.
Yes, I'll do that. Thank you. Much appreciated. And thank you again for having me. So really happy to be here. So.
Well, Joseph, thank you very much. Very insightful, and we appreciate your attendance. Thank you. The next presentation, 3 right turns to pavement preservation, treatment, roadway, timing, is presented by John Singer. John is an engineer of pavement technology at the Illinois Department of Transportation. Before joining the transportation agency ranks, John was a consulting engineer working on a wide range of projects, and he earned his Bachelor in Civils and Engineering from Bradley University. John, thank you for joining us today.
Thank you, John. I appreciate it. Let's get the PowerPoint up here. Before I get started, I wanted to thank the committee for the award yesterday. I apologize. I had to step away to do some interviews yesterday afternoon. I want to thank my staff for all the hard work that they've done this year and really helped advance a lot of the things that we've been working on at the department. So thank you to everybody. I think there was a question yesterday about the test track and why it was being put so far south. I wanted to make it clear that the test track that we are building is to basically certify inertial profilers. That's the main purpose of this. So we are only concerned with the surface characteristics. We are not necessarily studying the environmental effects of on the pavement structure itself. Now, we do get a benefit of it being further south as we have less freeze-thaw cycles. So hopefully that will buy us some time in having to do any maintenance and rehabilitation to those sections of roadway. There is a presentation that I did a couple several weeks ago on the RPUG website. Kind of gives an overview of what the track entails. We're looking to do a whole lot of testing with our non-destructive equipment and some pavement preservation research and other items, mainly on the surface. So getting into the main topic here for this slot, we have 3 right turns into pavement preservation. So kind of what we're going to go through on the outline today and what the presentation is mainly based on is how the Pavement Preservation Committee at IDOT reviews projects and kind of our philosophy in going through and picking appropriate treatments for the roadway. So for the first 2 presentations today, we're going to go through some Venn diagrams. And this is kind of showing the best way to get to our perfect treatment for the roadway. We have to have a good balance between timing, the right treatment, and the right roadway. And you could probably add another couple other layers to this to make it more complicated, especially with the timing. You want to maximize the timing of the existing surface to make sure that you're getting a full extent of the life of that surface before you apply anything to it. But you also don't want to wait too long to where you're shortening the life of your preservation treatment. So this is definitely a complicated topic. So first off, I kind of wanted to go through and define what pavement preservation is. There's a lot of different definitions floating out there, especially with federal highways and things like that. So the first one is actually from EDC 4, focus on pavement preservation. Pavement preservation is an activity highway agencies employ to maintain and improve a pavement's functional condition at a relatively low cost. And I think there's 2 key words in there that we need to focus on, and it's functional condition and relatively low cost. Pavement preservation is not intended to address structural issues or improve the structure of pavement in any sense. The second one is another definition that comes from federal highways. And basically we're looking more at a pavement preservation program with this definition. And we're using a bunch of different strategies in order to prolong and the pavement, improve safety, and meet road users' expectations. And then the third definition there at the bottom is the way that IDOT currently defines it in our Design and Environment Manual. So we're trying to extend the surface of the pavement before the roadway reaches a condition that requires rehabilitation. All right, so the first right turn that we're going to take is picking the right road. So there's a couple questions that we kind of go through and we ask when we're looking at these treatments and reviewing the projects that are submitted by the districts. Does the ADT support pavement preservation? Is the ADT too high? Do we have a bad mix of passenger vehicles and trucks and stuff like that? Will the maintenance of traffic allow the construction of preservation? Some of our very high ADT routes in the Chicago area don't necessarily lend itself to being friendly to construction with preservation treatments. So it's something that we need to keep in mind and pick our treatments accordingly. Does the pavement structure contain materials related to stresses? Decracking, ASR, and ACR cannot be addressed by pavement preservation strategies. And is it something that we necessarily want to address? In some cases, pavement preservation strategies can actually accelerate these materials related to stresses, and it's probably not a good idea in order to apply those. do we have all the proper toolboxes in order to address the pavement in question? I feel like IDOT's got a very healthy set of treatments that we can apply to roadways. Do we include all of them that are available out there? Not by any stretch of the means. And there are some agencies that are even more limited than what IDOT offers. So it's definitely something that needs to be considered. And finally, are there some features in the roadway that would preclude it from preservation treatments? And the first thing that came to mind for me was centerline rumble stripes. These are coming into play a lot more in Illinois with from the safety aspect, trying to keep lane departures at a minimum, but it also kind of inhibits the use of some of our pavement preservation treatments, because while they're really good at preserving the surface, they can decrease the effectiveness of these rumble strips. Like your microsurfacing and your cape seals and chip seals will tend to fill these rumble strips or rumble stripes, and therefore decreasing their effectiveness. You'd have to come back through and grind them again, and therefore reducing the cost effectiveness of pavement preservation treatments, and potentially the possibility that you're getting a good seal from the environment on that roadway. So moving into the second right turn, appropriate timing. You know, is this roadway still in good condition that we can preserve it and keep it in a good structural manner? Do we have a good balance of service life of the existing service and minimal distress to allow for pavement preservation? Are we at the point where we're going to maximize the effectiveness of the preservation treatment, and yet we've got a good amount of service life from the existing surface, whether it be PCC or HMA? Do we have enough time in the remainder of the construction season to apply the treatment? A lot of our pavement preservation treatments are very critical to are very subjective to the weather. So if we apply it too late in the season or too early in the season, we might be doing more harm than we are good. These are a couple photos from some of the submittals that we've received over the years. As we can see in the first photo on the left, we've got very little cracking. We've already sealed that centerline joint. As you can see, we've got a small transverse crack that's starting to appear about the middle of the picture there. This roadway is probably prime and ready for pavement preservation. As you can see, we've got oxidation occurring, and we might have some loss of some of the fines in the aggregate mixture that's on, in the HMA mixture that's on the top. We're probably just hitting that right window for appropriate timing. If you look at the center picture, we've got some pretty bad rutting that's going on. When the committee dug into this project, we went back and we looked at the history, and there was some very accelerated rutting in the beginning of this overlay's life, and we deemed that it was not appropriate for pavement preservation. There was a lot more that needed to be done to this roadway rather than just preserving it. And the last photo on the right here, I'm pretty sure this is obvious. We've got some issues with the pavement sliding, potentially debonding, and having some shearing tears in that surface. One of the good resources that I found out there is roadresource.org. This is the partnership between the International Surface or Slurry Systems Association, which is mainly covers microsurfacing, slurry seals, and chip seals, and crack sealant. And then the Pavement Recycling Association, ARA, So they've kind of got a larger conglomerate of industry that's the PRRA. They are the ones that sponsor this website. But this was a really good illustration and conceptual thing of staying ahead of the curve. So in the first 75% of the road's life, we have a drop of 40% in quality. And then over the next 12 years, we accelerate and drop another 40%. But if we apply pavement preservation treatments in the right time, we can delay this drop and hopefully keep our pavements in good condition for a much longer period of time. I want to emphasize that a lot of this stuff is conceptual. None of this is based on actual project data from one state or another. I was trying to pull some data from Illinois to see if I can match up with some of this stuff. And a lot of the stuff we do match closely. Some of the other stuff is a little exaggerated, but nonetheless, I think it's a good illustration of what can be done with pavement preservation if we apply it at the right time. All right, so the last slide on timing here. There is a delicate balance. Montana and South Dakota both seal cracks after the first year of construction of a new surface, and then place a chip seal or a microsurfacing after 2 years of construction. So they're of the mindset that they want to get on it really early, prevent oxidation and any weathering and raveling that could happen, and it seems to be benefiting them well. So in my deeper look into IDOT's projects and our selection, the districts around the state are generally selecting projects that have a CRS of about 6.5. That is well within the good category according to our CRS scale. So I think we're headed down the right road. We could potentially be picking things a little bit earlier to help kind of give the preservation treatments a little bit more of a chance at succeeding their most appropriate service life that we can give them. Other reports and studies have stated that approximately 5 to 7 years of life prior to a treatment is ideal. So on to the third right turn. So the best fit of treatments. In this one, we take a more deeper dive into the actual data that's available in IDOT's pavement inventory. We're taking a look at the surface age, the average annual daily traffic, the pavement structure, the distresses that are present on the roadway, the existing ride quality, rutting, and construction history. So this is a screenshot from iRoads, which is a database that IDOT has that contains all of its pavement inventory information. This is a route in, looks like Illinois 91 up in District 4. We've got the mile markers. We're starting at the county line, which is beginning station 0 and going a little over a mile into the county. We've got a composite pavement, which is basically HMA over PCC. And then we're showing our CRS rating there. That's the current CRS rating. I believe this project was from a 2019 letting. So we were 2 years behind on CRS. So the CRS was probably, at the time of construction, was more around a 7.3, 7.2, somewhere in that range. As you can see, we've got minimal distress. We've got some transverse cracking that's very tight, and still not a whole lot of additional distress associated with those transverse cracks. And the center line, or the longitudinal joint, starting to open up a little bit. That's why we've got the S1. Our ride numbers are still really good, as well as our rutting, and our ADT is very appropriate for pavement preservation. So going into the historical CRS, we can see that this road had received some sort of rehabilitation in 2015 that basically raised the CRS back up to a 9.0. The O's came back rather quickly, but that's kind of expected with composite pavements, especially if you've got joints and cracked panels below that are moving. Those O's tend to come back pretty quickly. But it looks like we've got a decent amount of life out of the previous overlay, and subsequently, hopefully with pavement preservation, we can do the same with the current overlay that's on there. We also go through and review the videos from our CRS workstations. We've got a contract with a vendor that goes out and collects the interstates every year, and the other marked routes of the state system every other year. So we'll go through and pull the video for the roadways, and we actually sit there and drive the entire sections and look to see if there's anything that's glaring that might cause concern for preservation, whether the treatment will work, whether it'll fail, if there's additional activities that need to be done with this project in order to help make sure that we are getting a good service life. So hopefully nobody gets car sick while we're driving this road. It is kind of interesting that we can drive the entire state system all from our computers these days. All right, so that was just a quick ride through one of the projects that we had over the years. And then last but not least, we go through the BDE guidance. This was developed by the Pavement Committee at IDOT. So I just kind of wanted to highlight the chart on the left is what is in the current BDE guidance. The chart on the right is an upcoming revision. We've got some things that we wanted to basically clarify and make some revisions as far as what the intent of pavement preservation is. As you can see, a lot of the NAs that were on the longitudinal joint repair have moved from NAs to NRs, and the idea and the concept behind this is that once we get to like an M3, which is our higher level block cracking, if we've got longitudinal distress as well as block cracking throughout the lane, it's more cost effective to treat the entire lane than just the longitudinal joint. So that's the concept behind the revisions and things like that. So we've done that for both the full depth HMA pavements. This here is our charts for composite pavements. And then finally, we've made some revisions to the concrete preservation. As you'll notice, there's a lot less that we can do for preservation of concrete treatments as opposed to asphalt based surfaces. So at this point, I'm open for any questions, and we can talk about preservation or the track or whatever we need to discuss.
I'm just giving a second so that people can submit their questions on the Q&A.
Absolutely.
Okay, I don't see any questions for now, but you guys can still, everyone can still submit them on the Q&A on the chat or raise their hands, and we can circle back to John Senger. Thank you, John, and I'm gonna give it back to John.
All right, thank you guys.
Thank you, John. Our third presenter this morning really needs no introduction, but he'll be presenting on the topic of cold in place recycling, when to open and overlay. Ahmad Al-Qadi is the Bliss Professor of Engineering at the University of Illinois at Urbana-Champaign. He also serves as director of UIUC's Illinois Center for Transportation and the Smart Transportation Infrastructure Initiative, as well as the Advanced Transportation Research and Engineering Laboratory. Dr. Ahmad's research efforts have developed new tests, testing specifications, and advanced modeling and simulation of pavement loading and crack development. He's a registered professional engineer and is a distinguished member of the American Society of Civil Engineers. Ahmad, again, we thank you. The floor is yours.
Thank you, John. I really appreciate it. And thank you for moderating the session too. This is an interesting project that we started working on this May, and I thought that it will be good to give an update about what's going on and where we're going to be going on this project, especially that cold in place is gaining momentum here in the state, as well as finding a way when to open this road for traffic. So the first thing I wanted to do here is to acknowledge the major help that we got from many different people. First, this is a project that is sponsored by IDOT and Federal Highway Administration, and John Singer, he is the technical review panel chair. We received tremendous help from Steve Worsfold and Ron Wagner, and Jason, who works with Heritage Group, as well as Stephanie Drain. So I really appreciate all the help in the coordination that they provided. Our ICT engineer were tremendous during the field project. So Uthman Muhammad Ali and Greg Renshaw. And special thanks for the students who went there to help as needed, Puneet, Javier, and Jose. And of course, most of the work is done by Trinchin Kao, Chiki Wang, and Lama Abu Faris. These are the people who are doing the work, and I'm just the presenter today. So first, to make sure that we are all on the same page, when we talk about cold in place, it's just a technique that will allow us to rehabilitate the pavement. It has been applied for secondary roads and recently has been used in Virginia for primary road, like the interstate highway. And this technique is really, I would say, desirable for several reasons. First, that the material is recycled in place and we can open the traffic in a very short period of time. And there is significant saving when it comes to the cost as well as the impact to the environment. However, there is a challenge there, which is when to open this road for traffic. As you know, that cold in place is just you recycle the material in place and you add to it engineered emulsion or any other emulsion. And there is, of course, amount of moisture that is involved in this. So in order to have this open to the traffic, we need the moisture to evaporate, and this is going to require some time. What is the time and what is the threshold? In Illinois, we're considering 2% moisture as the threshold to open the road for the traffic. And also sometimes we need to place the overlay at a specific period of time. So we need to know when the water has evaporated, so we will not be having stripping problems in the future, and also getting enough strength. In order to do that, there is few approaches. One is to look at the structural capacity gaining of the pavement itself. There is a couple of methods. One is the lightweight deflectometer, and the lightweight deflectometer is applying a load from a specific height over a circular plate and measure the deflection, and from that we will get the structural capacity of the pavement. The other one is the DCP, where you have a penetration of the pavement, which is very appropriate for granule material. And you raise a specific load and you drop it from a specific height and see what's the penetration, and that will be correlated to the CPR of the material. I wanted to mention here that the lightweight deflectometer, there is two of them. One is for granule material and one is for asphalt. And I will mention later here that the one for the asphalt is the one that it worked really well for us, but the one that has been used for granule material, it did not work as well. The other technique that's used currently in the field is to use the non-destructive testing, such as the nuclear gauge. And also there is the in situ density measurements using a sand cone, which means here that you dig in the hole and you place this with Ottawa sand, and knowing the volume, knowing the density of the Ottawa sand, we will be able to calculate or back calculate or by knowing the weight of the materials that we extracted from the hole, the density of that material. However, all these methods that I talked about, they are localized and they are just spot test and they are time consuming. Another approach is to have a continuous, rapid, and have good coverage, and that's by using ground penetrating radar. So for the use of ground penetrating radar for the moisture content monitoring, we need to do some field testing. We need to do some simulation as well as some theoretical and statistical analysis. So the steps went like this. In the same place that we are taking the materials for measuring the moisture in the field, we were taking measurements by GPR. It is known that from the GPR measurements, we can calculate the dielectric constant, and I'll explain this here in a minute. And we have the moisture content. The dielectric constant is increasing as the moisture content or free moisture content increase. From this, we'll be able to calculate the moisture content as well as predict the density. And ultimately, we're trying to give some indication about the threshold for the agency and the contractor when to open this road for traffic or when to have an overlay or place an overlay. So let me go back here and explain how the radar system, especially yesterday, there was a question about the GPR. So the GPR works the same as the radar that it's used to detect airplane. You send electromagnetic waves in the air, it hits an airplane, the airplane is from metal, it reflects completely back. We know what's the time that it takes for the wave to go and hit that airplane and come back. And knowing the speed of the electromagnetic waves in the air, which is the speed of the light, we'll be able to know the distance. We have the travel go and come back, the travel time, and we know in addition to that, the speed. So it's easy for us to back calculate or to determine the distance. That being said, that allow us to use this technique for many things, including detecting mines, because they have complete reflections if you have metals there, trying to detect where there is reinforcement in concrete, see if there is contamination in railroad ballast. And for pavement, we use this to detect, to find or to determine the density and to predict also the pavement thickness. So let's see how this works for pavements. Simply put, we have a DMI or digital measuring instrument, distance measuring instruments, and or a GPS. We like to use combination just for to make sure that we have all the data needed. It goes to a unit that is generate the pulse. The pulse, it goes to the antenna, and the antenna start now sending these pulses into the pavement. As the dielectric constant, or let's call it the electrical properties for the time being, for the pavement is different than the air. Some of these pulses will be reflected while the others will go through. Now, when this encounter a different material, such as the paste, some will be reflected, some will go through. So we collect all these reflected data or reflected signals, and we'll try to understand what is the dielectric properties of this material. So what you are seeing usually in the GPR is a van driving like this, and you have a complete keep reflection every time we are sending these waves, and you get a profile. You stack all these profiles together and you see something like you are seeing here in the screen, which appears as if, because of the reflections, as if you are seeing here the different layers of the pavement. So you're not having an X-ray here, it's just the reflections that it's happening at the interface. Let me maybe explain this in a little different way too. Let's assume that you have three materials. One of them is dry sand, one is wet sand, and one is saturated sand. Water is very lossy material, which means here that the dielectric constant of the water is very high compared to the air. The relative dielectric constant for the air is 1. The water is 81. Asphalt is around, depends on what kind of aggregate we're using. Asphalt binder is around 3. Aggregate limestone is around maybe 6 to 7, 8. Quartzite is around 4, maybe 5. So now when we have an idea about the materials we are dealing with, we know how fast this electromagnetic wave is going to go. So if you have a dry sand and the dielectric constant of that, let's say it's maybe 6, then the electromagnetic wave is going to go very fast. If you add to it water, then it will slow it down. It becomes maybe, because the dielectric constant is 15, it's slowing down. If you increase the water, it will slow it down more. And we can have this in this relation, which is the velocity of this electromagnetic waves is the same velocity in the air divided by the square root of the dielectric constant. And that's simply the whole concept of the GPR. Now we can take this and use simulation to see how the electromagnetic waves will penetrate into different areas. We use this concept here to understand, what's the dielectric constant of the material. So if we're using a GPR, we need to know two things. One is the pulse that we send and the pulse that it's reflecting. So the pulse that we are sending, we can measure it by have a complete reflector, which is a copper plate or aluminum plate, whatever. The metal is a complete reflector. So as we put underneath it a copper plate like this and have a complete reflection, now we know what's the incident wave or the amplitude of the incident wave that we are sending. When now we take the copper plate from underneath or from the top of the pavement and we send this electromagnetic waves again, you can see here, this is now the reflections coming from the surface of the pavement, and it will go up now. We can use this equation here in order to calculate what is the dielectric constant. Please notice here that these reflections are from the surface, and that's what we're going to be discussing today. And I'll mention maybe at the end what is the plan here to do it in the future to make sure that we look into the whole bulk of the layer. So based on this introduction here, there is something that we can use called the mixture theory to allow us to correlate the dielectric constant of the different materials to that of the asphalt. So look at the asphalt concrete here as a mixture. It consists of different components. Now the dielectric constant of the concrete is something we can predict from the reflections that I just showed in the slides earlier. The asphalt concrete consists of binder, which we know what is the dielectric constant, and we can know what's the volume of the binder in the mix from the mixture design itself. We know how much asphalt we put in, and we know what's the specific gravity for the asphalt, so we will know exactly what is the volume of the asphalt in the mix from the mixture design. The amount of aggregate is the same, but we need to know what's the dielectric constant for the aggregate, which we can back calculate. The dielectric constant for the air is 1, and we have the air void, which is unknown because that depends on the density. And we can add another variable here to make it even more complicated, which if you have moisture, and this is the case which we have in the cold in place. So that's why it's a challenging problem. So the whole idea of the mixture theory is the dielectric constant of the asphalt concrete is a function of the dielectric constant of each component and the portion or the partial volume of each one of these components. Like for example, the air is 5%, the dielectric constant is 1, the moisture, the dielectric constant is 81, and we have like, let's say 2% by volume moisture and so on for the rest. So if we know these components and their dielectric constant, we can also correlate that or equate that to the dielectric constant of the asphalt concrete. So this is the whole concept. So if now we know the dielectric constant of the asphalt concrete, we can know what is the density of the asphalt concrete, and we can predict that. 10 years ago or 12 years ago, we developed a model that has been used by many which is called the AL model. And this, maybe this equation, it appears complicated, but actually it is very simple if you look at the items that we have or the terms that we have in this. It's just depending on the dielectric constant of the components, the binder and the stone and the asphalt concrete, as well as the specific gravity of the different components that we have. So from that, we will be able to calculate the density. We know what's the maximum theoretical specific gravity or the big G. So we will be able to calculate the air void. So that's how we determine the density. So let's go to the field here. We started this project in May. And at the minute that we started this project, we have to go to the field because there were a few projects to start. At that time, of course, COVID-19 started. So I wanted to thank Greg Renshaw for all the safety measures that he had for the crew to go to the field and do the measurements. We have several sites that we looked at. 4 of them are called in place, and one we have the recycling happening in the plants. So it is a plant recycling called central called plant recycling. So I will discuss the one which one of these sections here. They are all similar. So I will discuss one of them. There were 3 of them in District 4 and 1 in District, yeah, 3 in District 4 and 1 in District 5, and then we have the plant one. So the first thing we did is went there, we sample, and we put this material in 2 Ziplocs and took it to the lab and do the measurements for the moisture content. And for the sand cone, I'm sure many of you are familiar with it. Just dug the hole and took the materials and of course put it in the Ziplocs. And then after that, put the sand, the Ottawa sand in to fill it in. We know the volume of the sand and we know the specific gravity. So we know what we placed in the hole itself. And that will allow us to calculate the density. Now, for the lightweight deflectometer, that was used to measure or to estimate the modulus by measuring the deflection from the load that it's applied. And as I mentioned earlier, we use 2 of these lightweight deflectometer. One is designed for granule material and it didn't work very well. And one is designed for the asphalt concrete and that worked really well. Actually, we used this earlier in the first warm SMA mixes like maybe 10 years ago, actually on a tollway project. And also we use the dynamic cone penetrometer to have an estimation of the shear or estimation of the CPR. As to the GPR test now, we did first measure the copper plate to know what kind of signal we are sending there. And we marked the spots. So we came at regular intervals and take measurements on the same spot. Again, every day we were doing the measurements, we have to do a calibration for the system, which I will be more than happy to discuss later how the calibration is done. So this is here some information or some details about the projects 61. It has 4 miles and it's 2 direction. We have 1 lane in each direction. The cross slope is around 1.5%. And that will impact the thickness that they were milling and placing also. And the length or the width of the lane is 13 foot wide. And we have 2 shoulders, one at 3 and another one is maybe similar. So from both sides. And we start the called in place recycling at station 827 plus 50. And ended at 1039 plus 05. And the depth of the called in place was 4 inch and engineered emulsion was used in this project. So if we look into the moisture content, we were taking the moisture contents. We have different samples. I'm just showing the averages here. And we took them at different days. Our plan is to take measurements over 7 days. Please note that we also collected the weather information because it rained in between sometimes, so that will impact our measurements. Another thing that it's really important for us to mention here is moisture, when it's free, it will give us a dielectric constant of 81. However, if it's bound, like if it's not breaking from the emulsion, it will give us a very low value because it is bound or it is strict from movement. So for the water to give us the high value of 81, it has to be very free to be moving, or the dipole of the water to be moving, so it will cause the polarization. So in this case here, it will be impacted by rain. It will be impacted also if it's breaking from the emulsion, or if it's still attached to the emulsion. So as you can see here, there is a trend with time. As time passes, these are different locations from the projects. They were separated because of the paving, like the first 4 were done on day 1, the other 3 were done on a second day. Now, the dielectric constant is not measured by GPR. The dielectric constant is predicted from the measurements of the GPR. And you can see here, there is a trend going on. It's more clear in the second day. You may consider that we became more, I guess, trained in the second round here. And the trend, you can see the breaking of the water is impacting the first couple of measurements, but after that, you can see that there is a trend of going down. This was more clear in the second day, that you have a trend going down very clearly in the measurements in the second day of paving, of course. What we did, we worked on a mixture theory. The mixture theory, again, it is correlating the components of the cold in place recycling material and its dielectric constant and portion of the volume, or the part of the volume corresponding to each material in order to come up with the dielectric constant for the whole cold in place recycling, or the bulk cold in place recycling. So we're working on this theory right now, but we are very, very encouraged. As you can see here, the predicted one, which is the red line, and the black is the one that we are measuring. And you can see here that there is very nice prediction that it could have been done, and this will be fine-tuned as we are moving forward. This is based on a corresponding copper calibration for the measurements. If we do the calibration overall, that for the whole maybe 7 days of measurements that we did, you can see here we have the similar trend, and again it was able to predict the reduction in the moisture. So as you can see clearly, as the dielectric constant or predicted dielectric constant is reduced, this means here that the moisture content has been reduced in the mix. Now if we look at the DCP, you can see clearly that there is a gain in the CPR of this material as the time passes in both the locations 1 to 4 and 5 to 7. And the same for the modulus. I'm showing the data from the lightweight deflectometer for the asphalt, because as I said, the one for the granule material didn't work very well. And you can see here that there is a gain in the structural capacity of the material as we move. Something interesting here is that the cold in place does not pick the density that people may expect. So here the density was usually in the range of like 80% or so. So the air void varies from as low as 16% to as high as 22. And that was even much, much higher when we were talking about the central plant. The density was not changing that much over measurements that we did in 3 hours to 7 days, as you can see here in this data. For the central plan, similar, it's 2 lanes and you have 1 lane in each direction, and the width is 12 feet and you have a shoulder of 3 to 4 foot, or 3 plus 1 inch, but in general, I guess it's like 3 to 4 feet. Same slope we have. We used engineer emulsion, and the thickness of the layer is 3 inches, and the length of the road was 2.85 miles. Again, here you can see that the moisture content is decreasing with time. We have this shaded here 5 days because we did have some rain event prior to the measurements. I wasn't sure it was 3rd day or 4th day, but we keep track of all this to see how this will impact our measurements. The dielectric constant, you can see that there is a little reduction here, and it was more pronounced in the 5 to 7 days. Again, if we implement the mixture theory, we can see here that we have some really good correlation. As the moisture is decreasing, the dielectric constant also is reduced. And again, we have a preliminary mixture theory that we're working on in order to calibrate it as we are collecting more data in order to be able to predict the moisture content more accurately in the field. This is again similar results, but we are using an average copper plate reflection over the days of taking the measurements. So let me here summarize by saying that the decrease in the cold in place moisture contents, it can lead to an increase of the mixture stiffness, and we can predict this and use it as an indication for the breaking of the water and curing. And this could be done by the dynamic compenetrometer or lightweight deflectometer, or we can use sand cone. However, any of these techniques are time consuming. They are spot measurements, so they are very localized, and they will not give us an idea about what's going on in the project. And they don't have a good coverage. So I think if you take measurements every 500 feet, still you are not covering, I guess, even 0.1% of the area, much less than that. So we don't have a very good coverage. On the other hand, the GPR will give us the coverage. You will drive at a highway speed, and it can be real, or right now it's near real time. So it can be done very quickly, but ultimately that's our goal, is to have it as real time by the end of this project. And we can, from that, predict the dielectric constant and correlate that using the mixture theory to the moisture content. So preliminary work shows some good success. Given here that the moisture does not just exist on the surface, we're working also on the modified CPM method, which will allow us to measure the dielectric constant for the whole layer. This is a method that we modified some time back, but we never use it for, of course, the cold in place recycling. So we will be able to modify this technique and try to use it in the second season for measurements. Again, I wanted to finalize by saying that our goal here is to take the GPR measurements, and from that, use that to predict the dielectric constant, regardless if it's going to be from the surface or if it's going to be using the modified CPM method for the whole pulp layer. Use the mixture theory that we're working on right now, and that will allow us to predict both the moisture content and the density, and ultimately provide you with the time when the road is ready. So the data that we get, it's going to be presented in a very simple way with the traffic light saying that this is not ready. When it's getting close to the 2%, we'll say that it's getting ready there. And if it becomes 2% or less, that's when it's ready to open to traffic, or if it's ready to override it. So with that, thank you so much. And I will be more than happy to answer any question.
Okay, Professor, we have an attendee that would like to ask you a question.
Sure.
That's Professor Ghassan Shuhab, so I'm going to allow him to talk right now.
Yeah.
Thank you, Dr. Al-Qadi, for a wonderful presentation. Just a quick question. Where does the 2% number come from? Is it from previous research you've done?
No, actually, this is something that it's known in the industry. Some states, they consider 2.5%. Some states here in Illinois, we thought about 2%, but actually, this is something that this project, after we are done, looking at the results from the LWD and the dynamic compenetrometer and how this increase with the reduction in the moisture, we're going to leave it to the TRP chair and the TRP panel members to decide if this number is going to be revisited. So if I'm going to answer you directly, I will say this is an arbitrary number that has been used by different states.
Okay, thank you, Dr. Qadi.
Yep.
Okay. We have time for a couple of more questions. If anybody has them, they can submit it in the Q&A button or in the chat or raise their hands. I did see a couple of questions for the previous presenter, John Zenger. Maybe you want to circle back on the questions from Fred.
Okay. Oh, you want me to do that, or there is a question from Laura?
No. Okay. Yeah, we can go to that question then. It says, how and to what magnitude does the variability in field mix thickness and density affect the accuracy of the data?
That's a very good question, Laura. Part of this, we have to run the sensitivity analysis. The thickness will impact the data, of course, impact the results, but we will be able to measure the thickness, so we can isolate that one. And when we identify the thickness, that's it. I mean, it's part of the GPR is measuring the thickness. So what is the sensitivity of that? That will be provided, but so far we have very, very accurate and control on measuring the thickness. So that's the first one you ask. And the second one is the field mix. I think this is also an excellent question. Let me put it in this way. If you have, let's say, the same amount of aggregate and binder and air in the mix, we will have a measurement. Let's assume that your gradation changed, which means here that the volumetrics of the aggregate change in the mix because of the segregation. Then we will be able to predict that and see that, because the whole idea of the GPR, it depends on the dielectric constant of the components and the volume of these components. So if this will change, we will be able to predict that and tell you that there is a problem. Now, these are different variables happening at the same time. So I can see where you are going with this question. Let's assume you're going to say the aggregate increase, for example, but at the same time, the moisture increase. That's part of the analysis that we're doing. So the moisture, usually it will be impacting this more than anything else when it's a free water. So to directly answer your question, yes, the mixes will be impacting the measurements, will be picked up by the GPR, and it will impact the predicted dielectric constant. The moisture, if it's considered for us, is part of these components. So we will be looking into this as one of the components in the mixture. That's a good question.
All right. I don't see any more questions anymore. So, and I just verified that John Zenger replied in the chat to Fred Cole. So I'm going to give it back to John so he can wrap up the session.
All right.
Thank you. Thank you, Ahmad. That wraps up our morning 3 programs, and we are getting ready to take a break, and I'm sure Ahmad will direct us as to this afternoon's timing.
Absolutely. So John, thank you so much. And our afternoon will start sharp at 1:30. So we will see you at 1:30. I know that yesterday we started at 2 because we ended at 12. Today we ended at 11:30, and we will start at 1:30 sharp. Again, thank you all, and we'll see you shortly.